one of the nice key features of this is that then the system will automatically resolve dependencies for you. So if I want to load a NIC driver, the NIC driver depends on MISC-MII, if it's maybe an Ethernet driver, and it will suck in the MII framework automatically for me and make sure that it is always available. And it will be impossible for me to unload that MII module as long as I have any other module in the system that has expressed this link dependency. And I'll need to do that in order to access any of the symbols that are in that MII module, for example. So when you're working in a source tree, one of the unfortunate things with illumos is that right now it's the makefile structure for the kernel subsystem is Byzantine. One of the projects I'd like to do is clean this up. I'd like to see someone else do. So you put your driver under UTS common IO. So it's a common. So the thing is, whoa, it's a common driver. Nice. Because it's architecture independent. It could go under Intel if it was an Intel only driver. IO, it's an IO. It's not for the IO subsystem basically. And then the name of my driver typically. So I have UTS common IO AFE / AFE.c. AFE is an Ethernet driver. And then now I have to figure out how I make the system aware of all this. I got to edit a bunch of these make files. And here's the list. I'm not going to show you the example. But you'll notice there's 1, 2, 3, 4 make files I have to edit to do this. And I haven't even touched the packaging, right? Which I'm not going to talk about the packaging, that's a different topic. But just to get the system to build the driver, I have to touch 4 make files. And then I have to populate, of course, the actual source. So, and you'll notice that this Intel driver makefile, that's not Intel IO, so I'm actually going to create 2 directories typically as well. When I build the source, there's a bunch of stuff on the wiki. This is basically a repeat of what's on the wiki. The unfortunate part here is this wait. That's a full build of the kernel. So don't do this on VirtualBox. VirtualBox does something evil. It makes that's where the days comes from. It's VirtualBox. There's something bad about pathological in the way the build works on there. But on typical hardware, on current generation hardware, you can do a build in 20 minutes. On older generation hardware, it's going to take longer. Now, you don't want to do that way if you can avoid it. So if you don't want to build the whole system, there is a way to do this, do just a piece. So what you can do is you do this make setup instead of, you do all the environment setup pieces, which you have to do. Edit the environment file, make sure that you have the compilers, right? All that pieces you're going to do. But you're going to do that just once for the workspace. If you have the time, go ahead and do a full build. But if you're in a real hurry, you can do make setup. The problem is when you can do just make setup, if you have any dependencies on anything besides headers, or if you want to run like lint libraries, if you want to run lint, you're not going to get that. So I recommend always just doing a full build first, if you're going to be, especially if you're going to be doing a lot of development in that workspace. But if you're in a hurry, you can just do make setup. And then you would CD, and I used AFE here as an example. AFE is an Ethernet driver I wrote ages ago. You would CD into that directory, and then you could just do make install. And you'll get either OBJ64 and 32, or debug64 and debug32, depending on how you initialized your environment, if it's a debug build or a non-debug build. And you'll note that regardless of whether it's debug or non-debug, it's going to build both the 32 and 64-bit modules for you by default. There are ways to override that in the makefile if it doesn't make sense to build a 32-bit module or it doesn't make sense to build a 64-bit module, but those would be not normal. I talked a little bit about register accesses. So when you create these things with DDI-RegsMap setup, you create a handle by which you access registers. You don't just read and write to them directly. And through the handle, you get a layer of indirection. One of the things this indirection gives you is it'll deal with endianness concerns for you. So when you allocate the handle, you tell it, the framework, this device is fundamentally big endian. Now, regardless of whether I'm running on big endian or little endian CPU, when I go and access it, the system will take care of making the endianness work for me. So I don't have to think about it. So I have one driver source. I don't have to have if-def, big endian, little endian scattered through my code. I have only one place I have to put this this endianness description, and it's in when I declare the attributes of the hardware. The other thing it gives me is also these interfaces, DDI get and put. I can use these in other ways, not just on registers. I can use them on memory that I've allocated for DMA. So for example, for accessing descriptor rings, where you also have to worry about endianness concerns. And I can use them, it doesn't matter whether I'm accessing PCI configuration space, I can use these to access PCI configuration space as well. Although there's a special version of functions you can use for PCI configuration space if you want to. Remember I said that DMA interfaces are different and unique because of the architectural differences. I've already mentioned the DDI put and get. You can use these here. Again, you work through a handle, and the handle defines the attributes of the region you're trying to access. Generally, for reasons, for a variety of reasons relating to performance, it was best if you know you're going to be doing a DMA of a space. If it works for your model, allocate the DMA memory using the DMA allocation functions rather than just do a kmem-alloc and then binding to it. And the reason is that I can now, when I tell the device the attributes of the memory, I will get my memory allocated in a way that I can do this ideally with just a single DMA region, and I don't have to go through, there's a, I can't remember the word I'm looking for. I can't remember this word. Basically, if I can't make it the memory that I get randomly from the kernel isn't naturally addressable by the device, then I have to go through a lot of extra pain and suffering, including an extra layer of copying that the framework will do for me. I would like not to have to do that, so it's best if I can allocate the memory or tell the system how I want the memory, how I'm going to use the memory. I'm going to use it with this device, so do it that way. A lot of times you can't do that if you're dealing with things coming from elsewhere in the system, but when you can. Cache flushing is one of the things that this is an area of lots of bugs. I see lots of bugs here. By the way, has anybody noticed I haven't said anything about using volatile? If I'm using DDI put and get, I don't need volatile keywords. So when you access memory directly, you may need volatile keywords to prevent the compiler from collapsing the code. Anyway, DMA sync allows you, is what you use to flush caches and buffers. I remember on the old Starfire systems, there was some assumptions that some drivers made that, oh well, I've asked for non-cached memory. I don't have to do DMA sync. Wrong, because DMA sync turned out on that platform to push through some intermediate I/O buffers as well. So that was interesting. So you should always call DMA sync. However, when you've allocated your DMA memory, if you've allocated it and told the system that it's basically non-cacheable memory, then the sync turns into basically a no-op. However, one thing that this doesn't solve is posted writes. Anybody know about posted writes? Don't know about posted writes? When you write out to a PCI bus, if you do not do anything, the system has no obligation to complete that write before it comes back to you. So if you need to know that that write is pushed all the way out, you need to do another operation on that PCI bus, like a read from the same register you just wrote to, that will force that to make sure that that gets posted all the way through the system to the device. So if you're working with PCI devices, you need to be aware of the PCI posted write problem. If you're not, you can get bit. And that's not, by the way, the PCI posted write problem, not unique to Solaris, illumos. That's PCI, right? I talked about 32, my slides are really out of order. the 32 and 64-bit interoperability problem. I'm going to blaze through this because we're almost out of time. There's basically there's interfaces you use to copy data in and out of the system and convert from 32 and 64-bit. You get to know there's an interface you can query the system. What is the application? Is it a 32-bit application or is it a 64-bit application? Once I know, then I can do some work to convert it. And there's some standard patterns for this. So just search in the source for multi-data model and you'll find lots of code. Or if you look at in the man pages for DDI model convert from, I think there's some examples in those man pages as well. Kstat is a nice lightweight framework for doing kstats. It's usually very lightweight. This is the cheapest way to do generic out-of-band reporting of your device, usually. One of the things is that when the system does do this, some devices go and they actually have a lot of work that they do as part of this. Try to not be one of those guys when you're writing your code. Try to make your kstat stuff very lightweight, because typically kstat stuff gets called a lot by monitoring functions and by all kinds of places. And they don't realize that some of the drivers have big amounts of code that get called. Solaris has and illumos have very rich debugging tools. The one that you most often will interact with is kernel developers called MDB or KMDB, which would be the in-kernel version, the modular debugger. And I have some really cool examples of this. One of the nice things is we have type awareness in the system, but we don't have source level. Okay? Type level information is really useful. Not having source level turns out to also be useful because the type level stuff is actually built into the system. And every illumos system ever deployed has the type information that is appropriate for that system built into those modules. So I can go look with MDB on that. I don't have to carry around a source tree with me to do meaningful debugging. So here's some examples of actually running. So there's these macros or these D commands. So I run prtconf. This is inside MDB. I grep for E1000G to find the instance of E1000G. I really need a laser pointer. From that, I get the address of the node. I can pass it to devinfo. Devinfo is devinfo $less. I'm actually calling a built-in macro, well, a macro that was created based on the type. So struct devinfo, it's expanding struct devinfo for me, and I grep for some things because otherwise I get a big long spew of stuff. And then from that, I can grab an address of the driver data, which will give me the soft state. And boom, I can look at the soft state. And look, I got a bunch of stuff in the soft state, and it knows these are very specific to this driver, right? It knows blink LED is a pointer to, and actually even it knows the ELF symbol. So it's done the ELF symbol mapping for me. So it's not even, I'm not even seeing an address, I'm seeing the name of the function that would be in that entry point for the Mac ops in this case, right? But this is very specific to this driver. But I had to know initially that there was a structure called E1000G, and that's what this $less E1000G is. I'm actually accessing the built-in type system of MDB. It turns out to be really, really flexible and powerful. Another example, just dumping a thread list, right? I can dump the thread list, and I piped it to head so that I could have the example fit. And then from that, down lower, you'll see that I took the address of one of these, piped it to the macro thread list, and I got a backtrace. So I can look at a backtrace of an individual thread. Here's another example. From the shell, I can send in some commands through the shell to MDB to dump. In this case, I wanted to get the interrupt, call the interrupt D command to dump the interrupts. So this turns out to actually be useful in system engineering debugging as well, not just kernel code debugging. DTrace, for those of you that didn't see Brendan's talk, you really missed out. There's a lot of material online around DTrace. Yeah, just some quick examples, right? So I can look, using the FBT thing, I can look at every time the E1000G interrupt routine gets called, and actually match two probes, entry and exit. These are automatic, it dumped them out. I didn't have to modify the E1000G driver to do this. The system did it for me dynamically. It modified the actual text segment of the code to insert these probes for me. Any function boundary on the system, I can look at this way.